And finally today we're going to look at 4.3, linearly independent sets and bases. So remember linearly independence, so V1 through Vn are linearly independent if and only if the only way to add them up and get 0 is if all of the scaling factors are 0. That's what it means to be linearly independent. There's no way to combine these to get 0 except for to scale them all down to 0. Okay, and so what that actually means for us, as far as what we're interested in this section, let's remember that how do we get a basis for what a basis is and how we get a basis for Rn, for the null space of a matrix and the column space of a matrix. Okay, so remember also that, so this is our first thing from before, also a basis is a linearly independent spanning set. So we may have a spanning set that is something that we start with and we're allowed to combine together however we want, but it's not a basis because it's not linearly independent. So let's combine these two notions together. So let's find a basis for col A, the column space of A, where A is this matrix. Well, remember that col A is the span of the vectors. So if these vectors were linearly independent, then it would be a linearly independent spanning set, which would be a basis. But if the vectors are not linearly independent, then it's in fact not a basis, and we don't need them all. So let's see what happens. How do we figure out if vectors are linearly independent? And so our question is, are the column vectors linearly independent? Well, the way we do that is the same way that we do anything, which is row reduce. Now remember that this one is one where our calculators get a little bit tricky because it can't row reduce something which has more rows than it does columns, so we have to add that extra column of zeros just in order to be able to row reduce. But if we do that, this is what we get. Remember that vectors are linearly independent if I get as many pivots as possible. If I get a pivot in every possible column. So, and that's not true here. I do not have a pivot. So there's no pivot in column 3. So the answer to that question is no. Right? I would need, there's not a pivot in every column. Since we don't have a pivot in column 3, that means that we actually don't need the original column 3 in order to span the same thing. So what that tells us is that the column space of A is in fact just the span of the first two columns. don't need them all because the third one can be created as a linear combination of the first two. So notice what we do. We take the matrix A, we row reduce it, we find out where the pivots are, we take the columns off the original matrix A, which corresponded to the pivot columns. And those form a basis for the column space of A. Right, so, and these two things here are a basis for col A. Now, as far as the null space goes, well, we've already done everything we need to do. The null space we get, remember, by finding the parametric vector form of the solution set to AX equals 0 and pulling off the vectors that we get corresponding to each parameter. Those things already are going to be linearly independent. Let's just look at one more example of that, just to keep track of it, but it's not any different than before. Let's find a basis for null A where A is this matrix. Which we still get by row reducing, but remember really what we're doing, we're row reducing, we're thinking about AX equals 0, that's the null space, so we really are row reducing this matrix with an extra column of zeros. However, when you put an extra column of zeros and row reduce, that last column of zeros always stays as zeros. So we really can just row reduce this matrix and add a column of zeros at the end. So 4 by 4. And this is what we get. So that's what we get when we row reduce it. And again, we're thinking about this as AX equals 0. So we're thinking about this as a column of constants at the end. And this is what we get. So now we need to change that over to a parametric vector form of the solution. And in order to do so, we read this as x1 plus x3 plus 3x4 is 0. x2 minus x3 minus x4 is 0. x3 is free, so let's call that t. x4 is free, so let's call that s. So this becomes x1, if I bring these things over, that's negative x3, which is negative t, minus 3s. x2 becomes t plus s, x3 is t, and x4 is s. Which means my solution is the vector x, x1, x2, x3, x4, which is negative t minus 3s, t plus s, t, s, which then we break up into each parameter. So we take a vector for the parameter t, and if we do that, what we have is negative 1, 1, 1, 0. And then we take a vector for the parameter s, which is negative 3, 1, 0, 1. Which means that a basis for the null space is the vectors that we get back in the end. Okay. So let's just look at one last example of the idea of basis in a more abstract vector space. So we'll look at one last example with a more abstract vector space V, which is P3, which is degree 3 polynomials. And I should be a little bit more precise. When I say degree 3 polynomials, what I actually mean is polynomials with at most degree 3. So this is third degree or less. That actually wouldn't be a vector space if I didn't include the or less, because if I looked at, for example, x cubed plus x squared, and then I subtracted, this is one vector, and I subtracted x cubed, which is another vector. Well, I need to stay in the set, remember. I need to have closed under addition and scaling. Scaling makes for subtraction, but this would actually just give me x squared. So when I say P3, I mean polynomials up to degree 3. So let's find a basis. For P3. My claim is that a basis is just these as simple as possible polynomials. Because any degree 3 polynomial is a linear combination of these. Right, so if I had a 2x cubed minus x squared plus 4, well, this corresponds to the linear combination scaling this by 2, scaling this by -1, scaling this by 0, and scaling this by 4. These things are linearly independent because there's no way to take any of these and add them up and scale and get to anything else. These are separated by so much space. I can't turn x cubed into anything else by just addition and scaling. So this is our standard basis for P3. We have a similar analogous standard basis for any other Pn. All right, and that's what we've got for section 4.3, and I'll see you next time.